It is done his PhD from Institute of Chemical Technology in Mumbai. If you are away, it is as good as an IIT for chemical engineering related sciences. Okay, you know, it was earlier called UDCT, University Department of Chemical Technology. Now it is called ICT. Okay, its alumni are really good and one of the best institutes in chemical engineering and chemical sciences. And since some years, they've started using biotechnology. Even IITs have started courses in life sciences. Even they have started, I think he's among the beginners to come out with a PhD, right?
Yes, yes, yes. So,
he will tell you more about himself and his journey and his PhD. Okay, so great. For the first
okay. Should I wait or should I start?
we come, you can just.
Okay. So I will tell you little about ICT and the for Energy Biosciences. So Center for Energy Biosciences is started in 10 years. So I was in the second batch of that doing PhD. So there they have a collaboration with DVT, Department of Biotechnology India, and they are working on biofuels mainly. So there are second generation, third generation biofuels. So what is second generation? It means making biofuels from the things which are not a feedstock. So you have learned that people are working on Jatropha and people are also working on they are working ethanol production from corn fields, right? But corn and other things are potentially and feedstocks. So if you are using them for ethanol, then there is a scarcity of food as well. So that's why this is second generation biofuel comes where you don't use sources from feedstock. You use other than that, like lignocellulose. So these are nothing but the wood. You decompose the wood and do the catalytic reactions, and then you go for ethanol production from that. Now the next comes in the line is third generation of biofuels, which is from algal systems, most likely microalgae. And how do people do that? They do molecular engineering, a little bit of tweaking of their metabolic pathways, so that they can they can produce an area of product from that. So mainly hydrocarbons like ethanol also there. Like you can also produce a lot of glucose out of that. So now this area is more of trending in India as well as outside India in US and as an alternative biofuels. So that's what my topic was, to develop an molecular tools or chassis for hydrocarbon production from sand bacteria. So basically, there are a few labs in India, which is like IITs mainly, who are working on metabolic engineering of algal systems and producing the very value-added compounds from it. So what algae do is they themselves has a very high value-added compounds. Those are called as carotenoids, and carotenoids has very good antioxidant properties, as well as they can be used as a food supplement or in cosmetic industries. So itself it is a very good biofactories. But if you do metabolic engineering in that and produce an array of products from it, so the demand gets more higher and higher. Also, these systems are also used for different versatile activities as well, like wastewater treatment. But that's all secondary things. You can also do wastewater treatment and then produce a lot of ethanol or something from that. Like genetically engineer a system, use wastewater as a medium and grow them, and then produce things. So it is like bioeconomic, like greener. So that is also some of the projects which are going from in DBT ICT Center, mainly from it is coming from algal systems there. So they have constructed a very good outdoor lab which is on the terrace, and you directly get sunlight from that there. So what most of the people are doing out in Europe or USA is that they are growing these algal systems in artificial light, mostly in tube lights, or they use area of this light stands or something, so that they can mimic the sunlight, but they only mimic the intensity of sunlight. Sunlight itself has a very broad spectrum and the intensity, so and it drastically changes from R to R. So that's a very different thing. That's what is going in India. That how this system can grow in outdoor or natural light conditions, and that was the first challenge in doing these things. Because apart from few industries and some institutes, no one is actually working on this system to go scale up. So that was what my objective was. One of the objective was, and to do hydrocarbon production. I will start with the building of a greener platforms. So the reason is that mainly whatever we use in day-to-day life, we use from a fossil-based products, right? So that is a lot of fossil involved in day-to-day life, and there are means it is producing a potential problem to our society because it is emitting a lot of carbon as well. So it is not good for the climate, and also because its demand is also ever increasing. But what it does is that most of the if we process this fossil fuel based compounds, okay, so whatever the residue which is left, it goes their effluent where left in water systems or in air. So it causes pollution in water, air, and land systems. So that's why there is now what people are doing is they are going for an alternative platforms, greener platforms. Now, in that they were asking that what kind of greener platforms you can use. So, means what we can say as a greener platform. So they come up with 12 principles of green chemistry. They said that the platform, whatever you are developing, it should be an accidental free. It should not cause any problems. Since in chemical industries, if any problem happens, there is a potential hazard to the health of people who are working there as well as the ecosystem which is surrounded there. So it should have the safer chemical synthesis, safer design. It should be energy efficient, and main thing is it should use a renewable materials, and it should be also a potential catalyst. Okay, so if there are few systems which are potentially taking few of these principles, like people are developing greener solvents so that chemical solvents will not be used and it won't cause potential harm to us. Then people are also going for a greener catalysis. They are using this is a chemical way of saying green. Then their alternative to this is people are using biological ways for the greener technology, like using yeast systems, bacterial systems. But as you know, if you use yeast or bacterial systems, and if they leave that particular facility, they can cause a lot of problems. It can if because they can cause a lot of potential hazard. So that's why algal systems is something that they are not toxic to the human health, and you can use it for our benefits as well. So that's why we were what my objective was, whether I am whatever algal systems I am applying, whether it is crossing all this, ticking all these principles or not, then only I can say I am using the greener platform and I am using it for producing high value products. So these were our criteria, what we said, that whatever platform we will use should be photosynthetic. As I have told you that it should use a renewable source of energy. It should be high growth rate, genome availability should be there because you can do easy genetic manipulation using those. It should be scalable, and if it is a scalable system, it is a sustainable system. So main point is it should be a sustainable system. Okay. So as I said, algal systems mostly take all these parameters, and that's why people are now using it for fuel precursors, pharmaceutical products, gaseous products. They are making isoprene is one of the high value products. It is a precursor for production of rubber tubes or in rubber industries. Then nutraceuticals and an array of different kind of applications as well, like CO2 mitigation, waste valorization, like treating a wastewater system as well. And then it can also be used as a human food and fertilizer. But basically, as you have learned that I am working on cyanobacteria from the title itself. The reason why we are using cyanobacteria is, if many of you know, that it is a simple prokaryotic organism, and because it is a prokaryotic organism, so it is a faster growing system than other microalgal systems, which are or other systems which are eukaryotic, because they need a lot of translational regulation or a lot of regulations are involved. Prokaryotic systems are basically very simple thing. Okay. So the another thing was naturally they are naturally competent. So if I choose a different eukaryotic system as well, I have to develop different molecular strategies to put my gene into that system, so as to produce some product from it. Okay. But naturally competent is something that I will, if I put DNA into their vicinity, they will directly take up that DNA and put it into their chromosome. So that is naturally they are not naturally competent, high growth rate, and they have polyploid genome. So they have multiple copies of single chromosome. Okay. So now, what if I take a gene from a plant? Suppose a plant is making some ice cream. Let's take an example of ice cream, which is a precursor. Okay. Now, what I will do is take that gene and I can put the gene into the my system. Now, because it is naturally competent, it will take this thing, but I have to also use some resistant marker gene for it. I think a lot of people haven't done molecular biology, but I will keep it simple. That suppose I took a gene from that plant and then I put this gene into the cyanobacteria, and in each of its chromosome, it will produce 4 times more of the product than any other system is. So I have a cells which has only single copy of chromosome or 2 copies of chromosome. They will produce a lesser compound than this compound, okay, than these cells. So that's why we are using cyanobacteria. And the thing is, beautiful thing about cyanobacteria is because they are so simplified, they can do state transition very easily. What is state transition? If I put these cells in any of the conditions, okay, and I keep on growing this, you keep on passaging this, they will get mutated over the time. They will get acclimatized easily. But if I use a different kind of system, suppose it is a slow growing system and not that easily transitioning, so maybe it will happen that in the process they will die, and I won't be reaching at that level. So simple example is I have started culturing in national artificial light system in lab under tube light. Now I take a system cyanobacteria to outdoor scale conditions where you are using natural light. Right? Now taking it from tube light to natural light condition is a very big transition. Right? Now if in this scenario if I use cyanobacteria and if I use microalgae, that the thing is that cyanobacteria, there are chances that even 1 or 2 cells of cyanobacteria get acclimatized out of 100. I start with 100, and if even 1 or 2 cells get acclimatized, then they will keep growing, and at the end, I will get a system which is very well acclimatized. Now, same I am doing with microalgae, and if I start with 100 and I have left only with 1 or 2, that 1 or 2 will take a lot of time to grow. So there is a possibility maybe they will grow in that condition or they will die. So basically with cyanobacteria, I know that they are gonna do that state transition. So same is with Chlamydomonas. It is an eukaryotic system, but now it is used a lot in this biofuel conditions, and they also because they also display this kind of state transition. So taking the advantage of these significant characteristics, people have engineered these cells for production of nutraceuticals, terpenoids, hydrocarbons, and biofuels, and edible vaccines. So nowadays it is much more trendy. But one of the much more big thing is that if you look at their whole pathway, so what people have done is people have engineered genes in their metabolic pathway and produced a lot of products like sucrose, mannitol, glycerol, and these are produced only in, I am showing only data of cyanobacteria. What has happened with cyanobacteria? People have engineered so many genes in it that over the time we have seen a lot of products from it, like isobutanol and everything, and we can say like these are greener products. Okay. So I am basically keeping my talk towards in ethylene because ethylene is a precursor for a lot of products. Especially it is using pipe and construction systems as also as a pure fuel precursor. So it is a very bigger market. So one of the things I'm displaying here is I'm looking for an applicative kind of research where I'm targeting one product and that might go to a commercial value as well. So I took ethylene here and I have started, and I have also done bisabolin, but I will keep it to ethylene because it's so much of a. So this is the roadmap. So for starting with the going for ethylene production, you have to start with right from the very scratch, developing and molecular tools for it, like using plasmids, what kind of plasmid you will use, what kind of molecules you will use, like what kind of promoter you will use to you make that product. So right from choosing that thing and developing an a vehicle for ethylene production to going towards genetic engineering of cyanobacteria. After that, going to the conditioning those systems so that they can So I can nurture those systems and they will go to the harsher conditions. And knowing that how the systems are itself within the system, now what I have done is I have nurtured them and then I have grown them. But what is happening within the cell? That's I want to know. That is called as acclimatization study, and then going towards an outdoor 100-liter scales, bigger scale. So first is promoter selection, and that is done by using a reporter gene. So reporter gene is something like you use a fluorescent gene to know that how much that product is been made by with the help of that promoter. Second thing is to produce an ethylene from cyanobacteria, and we do it by metabolic engineering. So we take a gene, we codon optimize that gene, we take that gene and put it into the cyanobacteria with the help of the molecular tools which we have developed at the first. Later, once we have built up that thing and a natural light condition, we want to know that whether these cells will sustain or not. And if they are not sustaining, we have to nurture them. We have to give them physio-chemical condition like growth, optimizing growth condition in such a way that they will grow very easily in natural light. Once they are sustaining in that condition, we want to know that how in natural light condition they are actually keeping up. And at the end, we are going towards outdoor scale of conditions. So now this is one thing is still now it was only biology involved. Okay, here it is a technical thing because we are using these things in a reactor system. So in reactor, a lot of things comes like how what is the aeration rate and what kind of reactor you are using. So that is something which I have done in collaboration with other people.
So do you use open bioreactors or closed system?
So we have two kind of things there. One is the laboratory, which is set up in itself at terrace, which doesn't have that high scale reactors because it's lab, right? So you can only go to like 20, 50 liters scale. So beside that only, there is also an outdoors pilot skills. Okay. So on the terrace only. So those are not in laboratory. It's an open systems and that can go till 100 and 200 liters. So we have both the things, laboratory as well as outdoor.
You are not making for edible product, so you can go for the raceway ponds as well.
So that's the issue. Why cyanobacteria haven't made up to raceway ponds, and that's what I will tell you. So there, what kind of issues comes when you do scale up? So first, I started. Actually, I have started with many different kind of promoters, but I will use one which is actually worked out. So this is a PTRC promoter, which is basically an E. coli promoter. Okay, we took it from E. coli and then put it into the cyanobacteria. The reason is I was working with cyanobacteria's own promoters, but when you do molecular biology, actually there is a lot of problems with optimization. So I was about to get that construct done, and it was done in the meantime. It took 1.5 years to get it done. But after that, we came to another in the when we transformed that thing into the cyanobacteria. When we put it into the cyanobacterial cells, it haven't worked out. So that's why I was parallelly working with the PTRC promoter. And what we were having that vehicle already, we have just used the promoter and used an reporter gene, and this is what I got after transformation. I got EYFP gene into the cyanobacteria, and these are the colonies 5 to 6. I have seen many colonies. I have also kept it to like after a lot of passaging. I have kept it to this 5 colonies only. So basically, as I told you that cyanobacteria is a polyploidy, so it is a benefit as well as a very big burden as well. So suppose you have 10 chromosomes in cyanobacterial cells. Now, only two chromosomes are harboring your this gene. Suppose I have transformed EYFP into that, and EYFP goes into just two chromosomes, not in all 10 chromosomes. Okay, so the chances are when there is a replication phenomenon happening, they can revert back to wild type if they don't like, or if that gene they don't think that gene is essential for their growth. Okay, that's what cyanobacteria can do. So you have to constantly keep them under pressure so that even after 12 passage, you will get a confirmed colonies that will produce your gene. Okay. Otherwise, at any time they can get into the wild type. So these are something which were done after 12 passages, after a lot of, after 2 to 3 weeks of continuously spreading the cells. Okay, and the confirmed colonies, or one of the confirmed colonies was then put into the flask. And when you took it to the flask as well, you have to keep it for a few days so that it will do. And then I have done the transcription and translation regulation of it, mRNA and protein level, fluorescence level, because it is an EVA RPG. This is yellow fluorescence basically. So mRNA is very good. You do RT-PCR for that. So I have done RT-qPCR for that thing. And what results I have got is that basically PTRC is a chemically induced promoter. So if you put chemical, then only they will work. Okay, they will allow polymerase, and polymerase can go and produce much of EVA, right? And that's why I thought that I will put IPTG, which is a chemical which induces that promoter, which tells that promoter that now you can produce a lot of EVA. Okay. So I have used different concentrations of that, but as you can see from both of the data, that there was no significant difference. If you put your IPTG or if you don't put IPTG, that's not going to produce any significant difference in it, and that's actually beneficial. The reason this is a nearly constitutive, the reason I am saying that is, now suppose you go to 100 liter scale, right? So you can't take that IPTG is very costly. Even at minute level, it is very costly. So such, if this is such kind of thing that I don't put IPTG, and even if it is giving my product, it is economically beneficial for me, because at 100 liter scale I have to put a packet into of IPTG into it, which is not feasible for me. So it's easy for me to keep the cells as it is and let light do the thing. So this is PTRC was feasible. So the second step was putting ethylene gene EFE. So now here something called as restriction cloning. You can do restriction cloning with the help of BAMH and EPAR, which is a restriction enzymes. You can this works like a scissor. They can cut the EYP gene and set EFE gene into it. It works on an overlapping principle. So EFE will have some overlapping sequences. So I will cut this both means the sites of EFE with BAMH one and EPAR one. But I will cut my EFE as well as with that, with BAMH one and EPAR one, so that it will produce an overlapping sequences, and EFE will go and sit there. So now PTRC will have EFE, and I have done same transformation into the cyanobacteria. And after final transformations, I have got this, that final product, that a cyanobacterial colony having EFE. So till here, I have what I have done is I have built a machinery which will now produce ethylene. So EFE basically produces ethylene. Now, thing is, cyanobacteria in normal condition they don't produce, they never produce ethylene, because they don't have to produce ethylene ever. Okay, but if you take a plant, but plant makes ethylene because it promotes growth in plant, and that's why you can take that EFE gene from the plant genome itself. You can optimize that for your system, and you can produce it in, you can put it into the cyanobacteria, and then cyanobacteria will make ethylene. So now it will make it. But the great thing is that people have also come up with this thing that now ethylene also promotes cyanobacterial growth. That is one of the positive things which happened in my system as well. So it is not a new thing that people are doing, producing ethylene from cyanobacteria. These are the list of people who are working on cyanobacteria for production of ethylene. But here there are two things. One is volumetric cells, and one is the light intensity on which they were working. These are very low light intensity. For example, if I give you how much light intensity the sunlight has, it is like 1200 to 1500. That's the number. Okay. And now you can see this is 50, 100, and maximum goes to 220. So these are very lab level studies, and they don't go to commercial level. Even though these people are trying to produce more and more of it. The second thing is they are restricting this thing to also ml till ml, and hardly any study is there in liters. Okay, So the problem is, this is not an e system or something that even at smaller scale you are making a lot of products. In algal system, that is one of the caveat where if you go it to the 200 liter scale or ratio pond, then only you will get benefits out of it. Then only it will go to commercial, because algal systems make very minute of the products. They don't as not like an e system which can produce ample of products. Okay. So that's why these were the challenges that as you go from lab from artificial to outdoor cultivation conditions, so you see lot of challenges which are increasing. Light is very high, pH is very high, temperature is rising, and in outdoor system you don't have any kind of control. So the temperature is variable, the light conditions are variable, and it is and basically this contamination won't be like fungal system or koi or system bacterial system, because for them to contaminate algal system they will need a lot of rich carbon source. तो मैं अगर ग्लूकोज डालता हूँ या कुछ शुगर डालता हूँ तो ही in that condition I will form contamination. Okay. So these contaminations are not from any other system, but it can happen from algal systems itself. Okay. So, like I am growing cyanobacteria or chlorella or algae, microalgae, and it is a very potential contaminant. Anywhere you go, it will contaminate anything. So the thing is, if you don't make some strategy, your cyanobacteria will get contaminated with chlorella as well. And many times हमको नहीं पता होता था कि क्यों contamination आ रहा है chlorella, because these were autoclaved systems.
So if we increase the means add more cyanobacteria into the wastewater ponds, then we can eliminate the cross contamination.
For the time being, you can eliminate the cross contamination because they can form pores. They have that thing that they can go into the dormant stage, and once cyanobacteria reach up to a certain level, you will see cyanobacteria dropping and chlorella increasing. And they outsmart cyanobacteria more. And the thing is that eukaryotic systems are robust most of the time, क्योंकि उनके पास रिपेयर सिस्टम बहुत अच्छा है, डीएनए रिपेयर सिस्टम होता है उनके पास जो बहुत अच्छे से वर्क करता है. बट प्रोकैरियोटिक सिस्टम बहुत सादा रहता है, उनके पास ऐसे कुछ रिपेयर सिस्टम नहीं होता है. दे विल इफ दे डाई यू वोंट सी देम. इन यूकैरियोटिक सिस्टम 3-4 महीने बाद वापस ग्रो हो जाते हैं कभी तो यूकैरियोटिक सिस्टम्स. देयर आर सम माइक्रोअल्गल सिस्टम्स which like you will see only a flask which is having only water in it, and after 4 months that cell again grows and you will see a red and green color. So that microalgae वापस आ जाता है compound system. So my challenge was to take it to this condition and sort these things out. So for that, what I have did is I started with engineering this system at lower scale, 250 ml, and slowly मैं बढ़ाते गए till 1 liter. I took it to the 1 liter photobioreactor, but then it haven't sustained. After 4 days, I saw that there is a death in my system, and it can be because of these four things: pH, oxidative stress, CO2, or contamination happening there. So you can't specifically say कि क्या हुआ है problem, but the thing is any of these four things might be causing the problem. Natural sunlight है, sunlight में stress होगा ही बहुत ज़्यादा. So इसके वजह से there is also part that sometimes because this is photosynthetic, तो electron transport बहुत ज़्यादा होता है इनमें. With that respect, अगर इलेक्ट्रॉन ट्रांसपोर्ट भी बहुत ज्यादा था तो वैसे ही ऑक्सीजन जो सुपर ऑक्साइड्स होते हैं या रिएक्टिव ऑक्सीजन स्पीशीज भी बहुत ज्यादा बनती है, और बिकॉज ऑफ दैट आल्सो दे डाई many times वायर कंटामिनेशन भी हो सकता है. So I wanted to devise a strategy where I can remediate all the four problems. Like I have to use something like a buffer system, use something which will increase the antioxidant, or use degassing. Basically, oxygen को निकाल देना पूरी तरह से system. Or and also I have to provide carbon source or pH based system. So if you use a specific pH based system, even in reservoir ponds you can grow monoclonal monoalgal systems. Means कि एक single pure algal system आप खड़ा कर सकते हो. The way he was saying कि आप reservoir pond में क्यों नहीं grow करते. So you want very specific pH setup चाहिए होता है उसके लिए, जिसमें सिर्फ cyanobacteria will grow and chlorella and others will not grow. So there is very बहुत छोटा मार्जिन होता है वो जहाँ पे इवेंट होता है. So we opted for CO2 purging and bicarbonate, sodium bicarbonate, which is baking soda. Okay. So and we have used different concentrations of it just to know कि क्या अच्छे से workout होता है. Now the thing is, हमने अलग-अलग different concentrations of bicarbonate देखा and we what we saw is कि specific हमारा growth काफी अच्छे से बढ़ रहा है and cells were also not dying. And also we have done the CO2 purging, but CO2 purging relatively उतना अच्छे से नहीं चलता. The reason is the more CO2 you put into the system, pH gets acidic, and that's why cells tends to die. But उसके opposite, if you go for the bicarbonate based system, तो वो alkaline होते जाता है all the time. While CO2 pure purge करते हो gas, so it gets acidic. So the next thing we wanted to know is कि growth तो अच्छा है, but how about the culture sustainability? Okay. So what we did is we went to the finding towards the mechanism of what is happening, why हमको growth ज़्यादा मिल रहा है. Annual sustenance was for months. Okay. The reason is कि cyanobacteria or कोई भी algal systems you take or plant systems, they have this carboxysomes. Carboxysomes what they do is काफी लोगों ने पढ़ा होगा कि CO2 concentrate कर देता है उस particular area में. The reason is ये ऐसा evolution इसलिए हुआ because in atmosphere itself उस time पे during when there is a deep entry and starting of the whole phenomena, उस time पे there is lot of CO2 in the atmosphere, but today it is only 0.04% CO2, which is very less. So कोई भी सिस्टम ग्रो नहीं कर पाएगा या सस्टेन नहीं कर पाएगा अगर इतना स्ट्रॉन्ग इतना कम CO2 हो. That's why they have developed this carboxysomes envelopes होते हैं जो CO2 को वहाँ पे around एक एंजाइम which is called as rubisco उसके around वो उसको concentrate कर देते हैं so that वो efficiently carbon fixation कर सके algal system. Now bicarbonate क्या करता है? Obviously the reason is कि जैसे तुम स्केल में हाई जाते हो तो CO2 कार्बन उतना ज्यादा लगता है सिस्टम के लिए. Right. Now what happened with my system is why it collapses because it was having very less amount of carbon to use or to do carbon fixation. Right. But that's what we started with कि ऐसा एक चीज है. But then we saw कि इसके membrane पे क्या हो सकता है. So there were transporters which help sodium and bicarbonate to go in. So this is called a sympro transporter. So दोनों को अलाउ करेगा अंदर जाने के लिए. So once bicarbonate goes in, this bicarbonate gets into the envelope of this carboxysome. अगर मैं CO2 देता हूँ instead of bicarbonate, तो CO2 because ये जो carboxysome का जो भी envelope है, its membrane potential only helps bicarbonate to come in. It won't help CO2 to come in. It's something kind of a regulation fashion that cyanobacteria has grown up. मींस अगर CO2 ज्यादा भी आ जाता तो टॉक्सिक हो जाता है सेल के लिए और अगर कम भी होता तो प्रॉब्लम होता. तो दे हैव दिस evolutionary fashion जिसमें उन्होंने only they favor bicarbonate to come in so that to keep it regulated very well. ठीक है. So that's why even if CO2 comes उसको bicarbonate में first it has to get converted and then it goes into the sample. But now we are here, we have a age, we are giving bicarbonate easy. So it goes in, Rubisco acts on it, gives more of a CO2, so ज़्यादा carbon fixation होगा. Okay. In this thing versus normal control या फिर आप CO2 purging करते हो. And also why the system gets alkaline is because sodium there is one more channel which helps to proton to come in. So जैसे जैसे proton cell के अंदर जाएगा और medium में सिर्फ OH minus ही रह जाएगा. So that makes more of an alkaline medium alkaline. And then from what it does is because of that more alkaline the medium is, it will capture more and more CO2 from the atmosphere. So जो CO2 atmosphere से वो absorb करता है into the medium, it again replenishes the bicarbonate. So it is a kind of a cycle. So bicarbonate never depletes that easily. So it's a win-win situation for us. तो एक बाइकार्बोनेट डालने से lot of problems get solved. The thing was that कि we wanted to know whether वही एक reason है. So as you know photosynthesis कैसे होता है. So there is a PS1 and PS2 in this photosynthesis. So यहाँ पे दो चीजें होती है. इलेक्ट्रॉन ट्रांसपोर्ट होता है दो तरीके का. एक होता है साइक्लिक इलेक्ट्रॉन ट्रांसपोर्ट और एक होता है लीनियर. लीनियर इलेक्ट्रॉन ट्रांसपोर्ट से बनता है NADPH और साइक्लिक से बनता है ATP. As simple as that. So when I put bicarbonate, and now I'm checking for bicarbonate system. What is happening with bicarbonate system for linear and cyclic electron transport versus control, जिसमें मैं कुछ भी नहीं डाल रहा. So in these blue ones is what I have done in natural light conditions. So सिर्फ इस पे focus करेंगे. So as you can see ETR2 and this is electron transport दोनों में बहुत high है. जब बाइकार्बोनेट डालते हो तो values are very high. तो इसका मतलब वेरी इजी कि ATP और NADPH ज्यादा बन रहा है इन बाइकार्बोनेट बेस्ड सिस्टम्स दैन इन एनी अदर कंट्रोल सिस्टम्स. देन नाउ इफ यू रियलाइज पूरा साइकिल कार्बन फिक्सेशन के लिए क्या लगता है. कोई भी कार्बन फिक्सेशन जब होता है, जब TCA साइकिल होती है, ग्लाइकोलिसिस होता है, TCA साइकिल होती है, उसके लिए क्या लगता है. यू नीड NADPH और ATP, राइट. सो जब आप बाइकार्बोनेट प्रोवाइड करते हो, व्हाट हैपेंस इज कि उनकी इलेक्ट्रॉन ट्रांसपोर्ट भी बढ़ता है, एटीपी और एनएडीपी पूल जो होता है वो पूरा पूरा सॉल्व हो जाता है और कार्बन फिक्सेशन भी हो रहा है. तो इट इज अ काइंड ऑफ अ टाइटर निश. मतलब इसमें से अगर मैं एक कंपोनेंट भी निकाल लूं, एनएडीपीएच भी नहीं बन रहा है और एटीपी इज आल्सो इज नॉट बीन मेड, सो दैट पूल इज नॉट सेटिस्फाइड, कार्बन फिक्सेशन भी अच्छे से नहीं होगा. So there was a one solution, bicarbonate डालना, and it solved a very big tighter niche. तो सारी के सारी cycle satisfy हो गई. So in that way cells were sustaining. So we started cloning the cells, making it for ethylene, then taking it for doing the nurturing of that with the help of bicarbonate. And now we are here where we are also knowing कि वो photosynthesis में क्या होता है. So एक PAM नाम पे एक इंस्ट्रूमेंट होता है which helps you to know कि these all readings what I have done is on that PAM system. So that helps you to know कि photosynthesis कैसे हो रहा है या कैसे cells sustain हो रहे हैं. And the last thing we go is towards outdoor conditions, to photobioreactor. So we have reached here. So मैंने systems को even higher scales पे लेके गया था 10 liter पे, and they were totally fine. They were sustaining with that. But before that, I wanted to know whether it is making ethylene or not. And you do it in two ways. You do SDS pitch of that. देखो पता है प्रोटीन पता लगने के लिए SDS pitch करते हैं, and then GCMS analysis करके productivity निकालते हैं. So in natural light condition, I was getting very good yield of ethylene in bicarbonate water systems. So ethylene has been made and system is stabilized. So everything was checked. So that's why we started growing the cells at पूरा lab भर दिया था with this thing, because when you go at 100 liters cell you need a lot of inoculum. So we have developed 40 liters of पहले cyanobacteria का पूरा inoculum, and then we went towards this 100 liters cells. So where we tried to put it into the reactors at 100 liter और फिर वहाँ से हम check कर रहे थे कि how much is biomass and how much is ethylene being made. And these were the condition differences. Okay, so the thing is कि जो वो terrace वाला lab है उसमें temperature was controlled, but the light source was natural light, sunlight. And in outdoor conditions जहाँ पे बड़ा pilot facility है 100 liter का, it doesn't have anything under control. So light is also variable और temperature भी variable है, कोई air condition नहीं है, nothing. So what we found is when we have done biomass production or more, so ethylene overall ethylene productivity or biomass both were good in this 100 liter steps. More than that, we were able to achieve this 100 liter PBR systems with 1.5 ml per liter of ethylene productivity. So this was the first system I have established after two years of my PhD. And this is where we put ourselves in the comparison 1 liter, 10 liter or 100 liter scales by natural light conditions. And these are the ethylene, so highest ethylene production as well as this time. So these were the concrete results that PTRC, using PTRC as a molecular tool, I have engineered ethylene into the cyanobacteria and then done nurturing, and then seen how it modulates the whole anti-nothing and successfully grown this in outdoor cultivation conditions. So that was the first, that was just the first objective. ऐसे मैंने और दो systems के लिए है मेरे 4 साल के लिए. But second time, as I have told you, कंसेप्ट थोड़ा अलग था. First time I have only established a system which was engineered and producing ethylene from it. Second time we use something called as one cell two well biorefinery वाला concept. Because in algal systems या कोई भी algal systems you are using, अगर आप सिंगल प्रोडक्ट बनाते हो तो आपकी इंडस्ट्री खत्म होने वाली है स्टार्ट होने से पहले ही. Because it doesn't generate that much revenue. Okay. So you need to target multiple products at a single time. चाहे तो वेस्ट वाटर में ग्रो करके फिर प्रोडक्ट भी बना लो तो भी you need to do lot of plus minuses, then only it will be profitable. That's why we were not seeing that much aggressively people going towards biofuel from algal systems. The reason is it needs a lot of money to go on. So from that perspective, what we have done is, as I said, they have that national high value metabolites also. Not only this technologies, but I can use this carotenoid as well. तो carotenoid का कैसा होता है कि even if I grow 100 grams in small this thing, I will get thousands and thousands of dollars from it because that much high value it has. उतनी उनकी activity भी होती है naturally. So काफी eye drops जो होते हैं उनमें भी ऐसे ही carotenoid products होते हैं. One of the example is zeaxanthin. Zeaxanthin is one of the carotenoid which has very high antioxidant property, which is now used in eye drops. So when you put it into the eye drops, अगर आपको कोई dystrophy हुई है या कुछ हुआ है, so it tries to normalize करने में help करता है काफी अच्छे से. And if you are not seeing correctly या बीच में थोड़ा blurred है, then also it helps a lot. That much strong properties है. One of another is astaxanthin करके है, जिसकी फूड वैल्यूज में डालते हैं फूड में बनाते हैं रेड कलर का होता है एंड इट आल्सो हैज अ वेरी हाई एंटीऑक्सीडेंट प्रॉपर्टीज. सो उनकी मार्केट में वैल्यूज बहुत ज्यादा होती है पर आपको कुछ करना नहीं पड़ता, जेनेटिकली इंजीनियर नहीं करना पड़ता, दे मेक इट इटसेल्फ. यस. सो बेसिकली जो पिछला सिस्टम आया है शॉमी में which was 7942 करके एक सिस्टम है, it was a fresh water system. This concept what I was working with was marine system because वो ज़्यादा robust होते हैं. तो cyanobacteria का और एक दूसरा strain है जो marine strain है. So here the problem was वहाँ पे मेरे पास वो vehicle था from the start only. I have to just use promoter and everything. यहाँ पे मुझे सब कुछ develop करना था because इस system पे कोई काम नहीं करता है. It is not that much evolved system. So from starting with all the molecular this thing and doing transformation right from the scratch we have started with this. And when you do that तुमको काफी सारे testing करना पड़ता है once you build a vehicle. So now how many of you have done molecular biology here? कितने लोगों का हो गया है course of molecular biology का?
8 semester 10 semester काफी लोगों का only first and
Only they are even affected by COVID. So online to work. So
Okay, because that's why I was restricting to explain all this because they might all know restriction cassettes क्या होती है and what are plasmids, right? So plasmid
already completed their dissertation.
yes, 10 sessions.
Some of them
Okay.
was, but then there are others.
Yeah, you must call.
So actually, basically, what you do is कि restriction cloning की मदद से you generate a patch by patch and plasmid. So ऐसे circular में दिखता है, उसमें diagram में वैसा होता है, but ऐसे नहीं दिखता plasmid. But by patch आपको plasmid के हर fragments को जोड़ना पड़ता है और वो PCR के help से ही होता है. So normal PCR करते हो and with the help of the primers, overlapping primers, patch by patch लोग ऐसे plasmids बनाते जाते हैं. In that patch, the people they put the restriction MCS sites, which are cloning sites भी डालते हैं, marker sites भी डालते हैं, कई दूसरे organism जो kanamycin resistant है कुछ उससे लेकर फिर इसमें डाल देते हैं kanamycin की, so that वो resistant marker बरकरार रहे. So you can put pressure on, but in cyanobacteria जैसे मैंने बोला कि homologous recombination होता है तो वहाँ पे neutral sites लगते हैं. These neutral sites itself come from cyanobacteria के chromosomes हैं. Neutral sites कुछ नहीं होते, evolutionary sites होते हैं जो अभी काम नहीं करते हैं. We don't have any work in cyanobacteria right now. Functional कुछ भी नहीं है. So I can swap them for putting my gene of interest to that. तो पहले में भी it is NSI करके था, which is neutral sites, पहले काम में भी NSI यूज होता है और इस काम में भी न्यूक्लियोसाइड्स डाले हुए हैं which is from 7002 जो मरीन सिस्टम है उसका ही जीन डाला हुआ है, इसलिए यहाँ पे NSI1 और NSI 5' और 3' लिखा है। So these are न्यूक्लियोसाइड्स दो जो स्वैप करने में हेल्प करेंगे होमोलोगस रिकॉम्बिनेशन जब साइनोबैक्टीरिया करेगा। तो व्हाट आई एम डूइंग इज कि अगर मैं इथिलीन लेता हूं और डाल रहा हूं साइनोबैक्टीरिया मींस वो इथिलीन क्रोमोसोम में जाएगा साइनोबैक्टीरिया के डायरेक्टली और उसकी कोई प्रॉब्लम भी नहीं होगा साइनोबैक्टीरिया को। तो जब तक आप और उसके साथ साथ कैनामाइसिन या कोई भी रेजिस्टेंट जीन की कैसेट होती है वो भी चली जाती है उसके साथ अंदर। So now that I can grow this transformed cyanobacteria into kanamycin while plate में. So basically, patch by patch, we have made this plasmid and we have done same thing. We have done the PTRC और EYFP दिया, इसमें भी डाला, but इसमें plasmid पहले से ही बना था और उसकी टेस्टिंग करते हैं. So whenever you make a plasmid, you have to test it कि उसकी efficiency क्या है. And lot of time people ask कि आपने अगर बनाया तो उसकी efficiency क्या होती है. तो आप कॉलोनीज ग्रो करते हैं बहुत सारे 100 to 100 कॉलोनीज हर बार पसाज करते जाते हो और देखते हो कि हाउ मच कॉलोनीज आर सस्टेनिंग टिल योर 12 पसाजेस और वो सारा एंटीबायोटिक में ही करते जाते हो। तो पहला जनरेशन आ गया, सेकंड आ गया, थर्ड आ गया, तो ये 12 जनरेशन तक वैसे करते हैं और फिर ये सारी चीजें देखते हैं कि हाउ मच कॉलोनीज आर दिस। सो मेरे 70 कॉलोनीज आउट ऑफ 100 कॉलोनीज 70 कॉलोनीज जिंदा रहे थे, तो उतनी अच्छी एफिशिएंसी मेरे प्लाज्मा and now then you have to keep a track कि मैं अगर साल बाद भी ये प्लाज्मा यूज करता हूँ तो कितनी स्टेबिलिटी रहती है। That also people ask how much stable it is.
So your plasmid was high copy.
हाँ. So same thing, same transformation protocol और same किया था। सिर्फ चीज इसमें ये थी कि because it is a marine system and Mumbai is on shore पे है, so I can use a marine based medium. So what we have done is कि इस बार nourishment में हमने marine based यही use किया था सब composition, ठीक different based on its physiology हमने different soil side किए थे but water sea water use किया था and the reason is कि most of the people क्या करते हैं कि salt water try किए करते हैं because not every region is in at a sea coast, right? So what they do is कि पानी में NaCl डाल देते हैं which is a salt water medium and then they grow this marine system into that. They mimic it. So the thing is कि वो बहुत ज़्यादा NaCl डालते हैं, like 25 grams of NaCl when you put in a liter only, वो dissolve तो हो जाता है, but that 25 grams cost a lot. मैं 100 liter system पे 25 grams का NaCl डाल के नहीं जा सकता है. I will need kilos of kilo. So I was having this advantage कि marine seawater use कर सकते हो, which is free of cost. You can go and take seawater. So economically beneficial. रोबोस्ट होने का ये मतलब नहीं कि वो कहीं कैसे भी ग्रो हो जाएगा। एट 10 लीटर सिस्टम इट वाज कोलैप्सिंग और बेसिकली द थिंग इज कि यही होता है कि मैंने जैसे पहले इसमें एस्टैब्लिश कर दिया, थैंक गॉड तुम लोगों को वापस नहीं जाना पड़ रहा है, मैं तो पूरा वही एक्सप्लेनेशन दिया। सो द थिंग इज कि जब तक वो निश कायम नहीं रहता है एनएडीपीएच एटीपी और कार्बन फिक्सेशन का कोई भी सिस्टम, कोई भी अलग सिस्टम स्केल अप पे नहीं जा सकता। ओके, सो any person who is working on scaling up of algae, they have to condition or nurture the algal systems. So basically, इनको भी हमने bicarbonate ही दिया था, but this time we have used some computational things to know कि if I put high amount of bicarbonate and low amount of bicarbonate, तो क्या होता है? So basically, ऐसे structures को they call it as flux balance. This is a kind of computational things. वो concentration बढ़ा के कम ज़्यादा करते हैं algorithms में and they produce this kind of things. So either what they have seen is कि ethylene and biomass पे if I go on increasing bicarbonate क्या effect होता है. So after a particular high concentration, the ethylene and biomass productivity कम हो जाती है. So the reason why ये कम होता है is basically they have done. These are the collaborators who have done that, and what they have found is this is the low carbon, मतलब कार्बन कम दिया है, let's say सिर्फ 3% कार्बन दिया है, यहाँ पे 5 और यहाँ पे 8, we will take an arbitrary numbers. Now 3 अगर मैंने दिया है तो कार्बन will flow out of this, but the thing is यहाँ पे जहाँ पे इथिलीन बन रहा है there is a very less carbon going in, okay, and that's why even carbon flow कम होने की वजह से बायोमास तो मेन क्वेश्चन था कि इफ आई सो मुझे कार्बन बढ़ाते ही जाना चाहिए राइट, बट एट 8 इफ यू सी क्या होता है कि यहाँ पे एक लीक होता है, लीकेज है फ्रॉम फॉस्फोफिनॉल पाइरुवेट टू ऑक्सैलिक एसिड। इफ यू इंक्रीज द कार्बन, कार्बन का फ्लक्स बायफरगेट होता है, so less of carbon goes to ethylene and much of a carbon goes to oxaloacetate. But if you are optimizing this at 5, तो ये कार्बन उस साइड जाता ही नहीं है। So we came to know that there is a particular threshold जहाँ पे bifurcation होता है। It might be at 7 or 8, but at low बीच में concentration, at medial concentration, the carbon only much of carbon flows to ethylene only. ये leak नहीं होता है यहाँ पे। So that's why if you keep on increasing bicarbonate, it is not like that कि ethylene भी उतना ही बढ़ता जाएगा और biomass भी उतना ही बढ़ता जाएगा, ऐसा नहीं होता है। कार्बन कुछ जगह पे लीकेज चालू हो सकता है कार्बन फ्लक्स का, and because of which you will not get that much concentration of ethylene even at high bicarbonate.
So is it possible to use some inhibitor for the enzyme catalyzing that step from that oxaloacetate?
Yes, people do that, but the thing is जो ये होता है PAP carboxylate study, you know, it is a kind of a rate limiting step in glycolysis. So the thing is कि अगर इसको inhibit कर देना तो नीचे कुछ भी नहीं होगा, cell will not survive if you do that. But the thing is कि even people try to suppress it, तो ethylene भी suppress ही हो जाएगा उसके साथ साथ. So the thing is, even if you want to suppress this kind of this thing, yeah, which is उसका ultimate effect इस पर भी देखता है मैं और second thing is also और एक चीज और is that कि मैंने जैसे बोला कि रूबिस्को ये कार्बन फिक्सेशन करता है, बट रूबिस्को का पूल तो उतना ही रहता है सेल में। मैं रूबिस्को का आई एम नॉट इंक्रीजिंग रूबिस्कोस पूल राइट, तो दैट मच पूल उतना ही पूल रहेगा, तो वैसे भी मैं कार्बन ज्यादा दूंगा तो इट वोंट वर्क बिकॉज़ ऑल द रूबिस्को इज नाउ ऑक्युपाइड विद मैक्सिमम कार्बन जितना वो ले सकते थे, तो नो कार्बन फिक्सेशन उससे ज्यादा नहीं हो सकता। दैट मींस इट इज अ काइंड ऑफ अ थ्रेशोल्ड, वो एंजाइम ही वहां नहीं है जो कार्बन फिक्सेशन उतना नहीं है जो कार्बन फिक्सेशन देता है। सो ऑल्दो यू कैन एक्चुअली इंजीनियर दैट और वो भी ज्यादा बनाता हो, बट वो आगे की स्टेज वो उतना टाइम नहीं देना। The thing is कि what is the role of bicarbonate? If you see first तो मैंने वही establish किया था पिछले बार mechanism में कि how carbon fixation happens with the bicarbonate, same thing happens, but then flow कैसे हो रहा है कि once bicarbonate goes in, bicarbonate multiple cycles में जाता है, एक single cycle में carbon flow नहीं होता, it goes to multiple cycles. So there is also called as MEP pathway जो terpenoids बनाते हैं, जो carotenoid बनाते हैं, ठीक, वो कार्बन उस साइड भी जाता है और वो कार्बन टीसीए साइकिल भी आता है। सो बेसिकली इससे आगे व्हाट वी हैव डिड इज कि दोस वर लॉट ऑफ सॉफ्टवेयर बेस्ड थिंग्स वी हैव डन, देन द सेम थिंग्स वी हैव फॉलोड इन जो पहले फ्रेश वाटर के साथ किया था डिफरेंट डिफरेंट बाइकार्बोनेट कंसंट्रेशंस का, सेम वी हैव डन इन मरीन सिस्टम्स एज वेल, और वहां पे वी फाउंड दैट 20 grams फर्स्ट इन फ्रेश वाटर सिस्टम वी फाउंड 5 gram per liter was best, here is 20 grams and rest template is the same जो 100 लीटर सिस्टम के साथ किया गया है, the वैसे slowly 100 लीटर के लिए but between that what we have done is कि कितना means ये carotenoids बन रहे हैं as a total carotenoids का, and at 20 grams per liter जब optimization हो गया था तो ये जो कल्चर था it was sustaining a lot of time for months and months it was sustaining. So then I went for carotenoid कितना बन रहा है, and I was getting maximum carotenoid in bicarbonate वाला in natural light. So basically what happens is if there is a lot of robust condition, in that condition to remediate that, these cells make lot of antioxidants like zeaxanthin, sunlight से बचने के लिए, या फिर वो ऑक्सीजन जो सुपर ऑक्साइड से रॉस बनते हैं उनको सप्रेस करने के लिए they make a lot of this antioxidants zeaxanthin, and that's beneficial for us. So we do HPLC of this and column separations, जब separation होता है उसकी मदद से we got a zeaxanthin, and इसके साथ साथ ethylene का भी हमने किया था, same thing किए थे।
You source the marine water directly from the sea.
See,
So, like you said that for resin pond, the ponds are susceptible susceptible to contamination. So if you source directly from marine water, it
There
might
was
contain
lot of contamination.
biological and chemical contaminants.
So what we do is we do autoclave of that. But as I told you that जब आप bicarb based system use करते हो तो it totally goes to alkaline condition. There सिर्फ आपका system condition हो चुका है अब तक. So what I do is कि मैं multiple passage करता रहता हूँ bicarbonate का. मतलब एक बार फ्लास्क में ग्रो हो गया बहुत ज्यादा साइनोबैक्टीरियम कि मैं वापस उसको पेलेट करता हूँ वापस मीडियम में करता हूँ. तो मैंने क्या किया अभी कि मैंने उसको कंडीशन कर दिया है तो इसलिए सिर्फ यही सिस्टम कंडीशन हो गया. अब क्लोरेला तो नया है इसमें तो ग्रो नहीं हो पाएगा क्योंकि वो कंडीशन नहीं हुआ है सिर्फ साइनोबैक्टीरियम कंडीशन. तो दिस गोज टू द पीएच ऑफ 8 to 10, sometimes even it touches 11, but only cyanobacteria can go at certain alkaline condition because I have conditioned them to do that. So इसी की मदद से I have done the 100 test reviews to this also. So template same है most of the thing क्योंकि उसके पीछे का जो mechanism था वो same था. Same template can be followed on all the most of the algal systems. Like even Chlamydomonas I was working with, which was microalgae. It was a kind of a transformant which was came from Germany itself. तो वो एक प्रोडक्ट बनाता है बिसाबोलिन करके which is very high in perfumery. तो उसका बिलियंस एंड बिलियंस डॉलर का मार्केट है. सो बट द थिंग इज कि क्लैमाडोमोनास आज तक कोई 100 लीटर पे कर नहीं पाया है या कोई हाई स्केल पे या नेशनल लाइट कंडीशन पे लेके नहीं गया है. देयर आर वेरी फ्यू पीपल्स एंड दैट्स आल्सो नॉट एन इंजीनियर्ड थिंग. मतलब एक इंजीनियर्ड सिस्टम एंड एक कंट्रोल्ड सिस्टम में बहुत बड़ा फर्क होता है कार्बन फ्लक्स में भी. सो जितना वेल अगर मैं कंट्रोल वाइल्ड टाइप को लेके जाऊंगा दैट डज नॉट मीन कि मेरा जो भी ट्रांसफॉर्मेंट है वो भी नेशनल लाइट या हाई इसमें कल्टिवेट हो. सो इन दैट वे बहुत कम रिसर्च होता है क्लैमाडोमोनास में. पीपल हैव डन इट फॉर हाइड्रोजन ग्रीन हाइड्रोजन बट वो खुद का एक इन्वेसिव प्रोडक्ट है. इट इज नॉट समथिंग इंजीनियर्ड सिस्टम. So what basically मैंने अलग से किया is I have took engineered system in outdoor conditions. So that was the different thing. The thing is also कि most of this इसमें मैंने जो gaseous product एक use किया so उसमें trapping है ऐसा कुछ नहीं लगता है. एक vacuum based system होता है जहाँ पे आप trapping करते हो. ये नीचे वाले system में बिसाबोलिन में actually आपको solvent डालना पड़ता है. So इसलिए उसको मैंने एक पर्टिकुलर स्केल तक ही लेके गया बट आई वाज द फर्स्ट टू डू इट इन आउटडोर कंडीशंस. एक इंजीनियर क्लैमाडोमोनास को एक आउटडोर कंडीशंस में लेके गया था. सो दैट वाज व्हाट आई हैव डन. मैं इससे बहुत ज्यादा कम किया बट मैंने इतने रेस्ट्रिक्ट रखा. सो बेसिकली the thing is if you see this journey how CMB cell and molecular biology helped is most of this is molecular biology work. So the first year I went to ISO Pune, जहाँ पे I was working under गायत्री. और गायत्री मैम जो थे वो just join हुए थे as a molecular biology करने के लिए उस टाइम. And weeks after weeks, first week, second week हम हर दिन molecular biology करते ही जाते थे. And we used to get lot of colonies, but there were lot of problems कि PCR सही से वर्क नहीं होता. आपने थ्योरेटिकली पढ़ा है बट सच में चीजें वैसे नहीं होती मॉलिक्यूलर बायोलॉजी. जो भी बुकिश लिखा है वैसे नहीं होता है. देयर आर लॉट ऑफ थिंग्स व्हिच यू हैव टू ऑप्टिमाइज योरसेल्फ लाइक राइट फ्रॉम एनालिंग टेंपरेचर से लेके तो जो आप इनका एलोंगेशन जो भी करते हो कितनी साइकिल रखनी है हाउ मच साइकिल रन शुड बी देयर नंबर ऑफ साइकिल्स. सो काफी सारे इवन प्राइमर्स कैसे मुझे ये करना है. सो at that time in first year and of bachelor's itself I was knowing that thing. Okay. So वो काफी अच्छे से किया था. And second year also third year also when I went to Guwahati IIST यहाँ से गया था और यहाँ के ही लोगों ने मुझे हेल्प की थी वहाँ पे सब एप्लीकेशन से करने में. So there I have done microbiology की techniques and plating was very good. So the guide was happy with the kind of plating I was plating में करता था क्योंकि contamination इतना आता नहीं था. So the thing is we were able to do this because हमको summer trainings मिलते थे and we used to do lot of things but यहाँ पे जो theoretical stuff भी बहुत help हुआ. And then I went to the interview for PhD interview के लिए. So यहाँ पे एक end में at the end of this thing proposal लिखने बोला था. and I was a big fan of quorum sensing.
Now this is important.
So I started with quorum sensing. I was loving quorum sensing so that कि मैंने पहले से आखिर के सेमेस्टर तक quorum sensing के ही presentations दी जब इधर presentation देने बोलते थे तो. So I have proposed that कि जो भी microbiota आप use कर रहे हो plant growth के लिए वो इस तरह से काम करता है कि वहाँ पे you have to engineer that bacteria so that वो एक particular product की AHL बने. AHL are these chemicals which help in quorum sensing. So this is a crosstalk between the bacteria and the plant itself. और if you are able to tweak that मतलब आप उनकी बातचीत में घुस के इसको क्या बोलना है उससे वो ये करते हो. तो plants give flavonoids to this, they do quorum sensing and you so ऐसे ही देना चालू रहता है दोनों में म्यूचुअलिज्म है दोनों ठीक है. सो ऑन दैट बेसिस मैंने कंपाउंड का प्रपोजल लिखा था टाइमलाइन लिखी थी जैसे कि यहाँ के फॉर्मेट में बताया था. एंड द गुड थिंग वाज आई वाज नॉट हैविंग थीसिस एट दैट टाइम बट आई वाज हैविंग प्रपोजल और मैंने वो प्रपोजल सबमिट किया वहाँ पे जो भी सारे लोग बैठे हुए थे जो और फिर दे स्टार्टेड टू आस्क मी अबाउट quorum sensing and the regulation basically. So the great thing was कि मास्टर्स तभी खत्म हुआ एंड एट दैट टाइम एडवांस मॉलिक्यूलर बायोलॉजी जो 5th सेमेस्टर में होता है they teach you a lot of about transcription and translation regulation in eukaryotic systems. So at that time only थोड़ा मुझे ये था कि अगर ऐसा प्रोडक्ट प्लांट के पास जाता है ऐसे केमिकल तो किस तरह का रेगुलेशन होता है क्योंकि प्लांट बायोलॉजी भी एज ए इलेक्टिव सब्जेक्ट था और वो भी 5th सेमेस्टर में काफी एडवांस में पढ़ाया गया था. So at that time तो वो थोड़ा कोरिलेट करके I was giving answers. But the thing is that thing gives me a little edge over other people. But also कि one of the faculty जो मेरे गाइड है उन्होंने मेरा CV बहुत अच्छे से चेक किया and she was very happy that उसमें molecular biology बहुत ज़्यादा किया हुआ था and hands. So उन्होंने क्या शर्त रखी कि I will keep you as a GRF. So GRF is not a PhD, it is a junior research fellow, ऐसी ट्रेनिंग के लिए. And she said कि I will see कि first 2 week में जो तुम molecular biology करेगा, उसमें तेरी कितने अच्छे कॉलेज और कितने अच्छे प्रैक्टिस है, उस हिसाब से I will enroll you in PhD. So I said okay क्योंकि मेरा तो already प्रैक्टिस काफी हो चुका था और theoretically she was also impressed. And I started with this thing. So मेरे mentor was very happy because उनको ज़्यादा चीजें बतानी नहीं पड़ी मुझे. I was regularly doing that. And he was transferring one of the gene which is called a CRTR जो इसमें ही है साइनो की जीन है कैरेक्टरॉइड ज्यादा बनाने में हेल्प करती है फ्लो फ्लक्स टुवर्ड्स कैरेक्टरॉइड बढ़ा देती है एंड ही वाज डूइंग दिस मॉलिक्यूलर बायोलॉजी और जानना चाहते थे कि कितने कॉलोनीज आ रहे हैं ही वाज जस्ट टेस्टिंग ऐसे करता है. तो वी हैव डन ट्रांसफॉर्मेशन और कॉलोनीज आई कुछ दिन बाद और हमने जस्ट 10 कॉलोनीज उठाई उसमें से. So there are a lot of colonies, but 10 उठाई and we have done colony PCR of that. 10 में से 8 colonies means were positive. So my mentor said पप्पू पास हो गया, तू जाके तेरे सर को मैम को बता दे and he was very happy. Go and tell your ma'am that. So I went to ma'am. She said okay और एक दो बार ऐसे रिजल्ट लाके दिखा मैं ऐसे लोग. So from that the journey started, but it is because of this whole journey and the theoretical stuff which I have done over the years. I have learned कि course का curriculum ही इतने अच्छे से ये हुआ था कि it helped me to go and answer those things. So वो एक चीज थी. Second चीज थी कि ये भी right है कुछ लोगों को ऐसे this thing is कि I was also very much this thing कि यार बाहर जाके PhD करते हैं या ऐसे करते. See, since I have finished PhD and doctorate and working here, I will tell you what's the differences. PhD में सबसे main चीज ये होती है कि what kind of guide and what kind of work it is. But first thing is what kind of person you are under. Okay, if a guide is supporting and you are enjoying this thing, so basically मैं ये बोल सकता हूँ कि ये 5 साल मैंने enjoy किए हैं, survive नहीं किए हैं PhD के. And the only thing you can do is.
That's a very big thing, huh? Most of the people, when they do PhD, they think that they have to just survive here. That means whatever he has been doing, he enjoyed.
Yes.
And maybe your guide must be very supportive. That's a very important thing. Because if that is not there, and maybe the way you impressed her, maybe that is
But
the
doing PhD in India also is definitely not bad. I mean, you got,
So
if the project is good,
thing
you
is,
have
I'm
established
saying
yourself as a scientist. You can even start from India. Nothing.
you what you are doing is
also you
basic.
don't something new also, and can have your own
Yes, most of the
model.
model studying. So we can do that, but the problem is that we heard a lot of things, and because of that, we block so many things coming our way now. And वो सारी चीजों को focus में मतलब एकदम the thing I have learned when I was doing work is कि when I used to go to lab at summer training, I was so open that मुझे ये करना है, जाके काम करना है, मजा करना है. So I used to then it automatically like ऐसे हो जाता था कि वो long hours work होता था, रातों रात काम करते थे, but वो कभी burden नहीं हुआ. The reason is I used to love that long hour thing. So the thing is कि तुमको PhD करना है या नहीं, या research में आगे जाना है या नहीं, is basically when you do this kind of training and everything, that कि तुमको काम करने में मजा आ रहा है, if you are that person कि तुमको काम करने में बहुत ज्यादा मजा आ रहा है, means कि तुम बहुत interested है उस चीज में, and do not restrict yourself with other lot of things कि यार इधर ही गया तो मैं ये मैं बहुत सक्सेसफुल होऊंगा और all those things. The reason is कि यही अलग चीज मैं कहीं और करता हूँ तो मैं भी उतना सही नहीं कर पाता जितना यहाँ पे मैं कर पाया. And the reason is also, so basically I'm telling you कि थोड़ा attitude वैसे grow करो कि बिंदास काम करना और बहुत अच्छे से काम करना है. Don't restrict yourself to this. There is no exact formula to anything. The people you are thinking कि मैं हार्वर्ड जाके बहुत अच्छा करूँगा, if you are mindset and your attitude is right, you can grow anywhere, you can do anything. Very nice. Very nice. खुले दिमाग से काम करो अच्छे
Finish
से
your
कुछ
PhD.
You have to say 4.5
Yes,
years.
he finished PhD with good
Complete
papers.
PhD is something very great.
Very great. Yeah.
Very great. That's what I told him when he met me. That way, very
So,
good.
one question. For microagriculture, why did you choose ICT over CSM CRM?
CSM CRI is basically working a lot on macroalgal cultures alone. They have expertise in macroalgae काफी ज़्यादा. So basically वो किस तरह का काम करते हैं कि वो cultivation पे ज़्यादा ध्यान देते हैं, molecular biology और metabolic engineering पे नहीं देते. They don't have that expert. So हर everything in India के अलग-अलग labs में, some people are focused on cultivation, while some people are focused on only metabolic this thing. Here the focus was both. So you have to do it with metabolic engineering as well as उसको scale up करके grow करना है काफी. What happens with CSM CRI is they work on that macroalgal seaweed का ये food and feeds. And if anybody, so इसमें भी जो algal biotechnologist होते हैं उनमें भी काफी सारे fractions. कुछ molecular biology अच्छा करते हैं तो कुछ लोगों को biotechnology अच्छी लगती है. जैसे कि सिर्फ macroalgae को grow करना and take out lipids, EPA and DHA out of it, which are very high, वो भी high value products हैं काफी सारे.
Triacylglycerol.
Yes. So ये जो कुछ जो है सिर्फ इधर तक ही उनका आइडिया ये होता है कि वो एक्सपर्टाइज इसमें है. तो CSM CRI is basically expertise in growing, cultivating at higher scales. They are not expertise in metabolic engineering of the systems. While ICGB is also one of the very famous institutes, and it's at New Delhi, and it works on metabolic engineering of macroalgal systems and cyanobacteria. So ये दूसरा और एक काम है. इसके बाद में Chlamydomonas को भी जब मैंने इस तरह से किया था. So one of the person collaborator with me was Pawan Jutru, जो ICGB के थे. But उनकी लैब सिर्फ restricted है metabolic engineering करने के लिए, very specific to building up metabolic flux analysis and क्या क्या metabolic profile बनती है. So fatty acid में कितना fatty acid बन रहा है, अगर मैं उसको ये कार्बन दूंगा या नाइट्रोजन दूंगा, वो scale up cultivation नहीं करता. So there are these patches where some expertise in this, some are expertise in this, but here you get everything. It was a mixture of everything.
Another point, what I was talking to him, he said that it is not important. Like for him, CSIR was not must. It is very few institutes in India. Like all other institutes, you have to have CSIR. So this is also a good opportunity. Those like your seniors also, maybe you people as well as your seniors who are looking for this, not
PhD
completed the
positions,
CSIR, they can also approach. But this doesn't mean that don't try for CSIR. You have to, all of you have to write CSIR. And the only thing which I am not satisfied with my CMA students is that very low rate of CSIR clearance.
I told them, ma'am.
And this is not true because, like in the sense,
More
the
people
kind
are
of
giving
the
back,
kind
most
of
people
things,
apply.
the kind of syllabus is there, and the kind of teaching you people have, you should certainly be able to clear the CSI. But if you are not doing it, means you are not taking them.
They're not applying, madam. They are giving only.
They are not. Some of them not giving. Some
Not
of them
giving.
trying to give, but then they are not at all preparing. हाँ बोल दिया मैडम ने चलो अप्लाई कर देते हैं बट अप्लाई करने के बाद में पढ़ाई नहीं की
अरे
पढ़ाई
वो
नहीं
last
करने
2-3
के
years
बाद
के पेपर
so
देखो.
this is where you people have to be very clear. बाहर जाना है जाओ. Nobody is saying no.
This is
But
one
this
certificate
India
help
also
you
has lot
anytime.
of very good
Yeah.
institutes and lot of very good opportunity for you. So दोनों नाव पे अच्छा नहीं है. दो पैर दो नाव पे नहीं रखना चाहिए. But till you are not getting anything, you should try. And
And
wherever you
sometimes
feel
even
that
abroad
it
they
is
say,
good,
yeah.
then
No, abroad
then
also
go
some
ahead.
people, if you have cleared CSM, they know the value of that exam. So they prefer to take it because, okay, you cleared that high level exam of India, means you are really good.
And for 10 semester students, how many are sitting here? Only 3. Very bad. So you have to see the project proposal has helped him. So take this very seriously. अभी क्या है थोड़ा डाइल्यूशन होता चला जा रहा है. People are not interested. अरे लिखना है लिख दिया. That's not the thing. Taking that kind of interest, yes, this might help me. So you should have now you can like you are already in 10th semester. You probably have some idea that where I would like to go. So just choose that kind of project proposal, write that. So when you are going for PhD entrances, it is going to help you because you already have something in your mind to talk to them, and that is certainly people are going to be impressed because of that. 100%. Even if I am in the interview board and somebody will come, like I will tell you, Nitish, one of my PhD students, when he came for our this thing, one of my projects interview, he already has written one paper, and we were very impressed because and only MSc and that too from I think Ajmer. Not like कि बहुत जगह से आ रहा है ऐसा कुछ नहीं. And then he already had that paper.
But it shows that he has
And
scientific
yeah,
this thing.
so Naresh was so happy, I was so happy, and then he selected me. And now he is in Canada
And
doing
he did very
excellent.
well, yeah.
So wait, it certainly helps. And as he said, one more very important point what he said. When you are doing this trainings and other thing and when you are doing your dissertation, you know that whether I am really interested in this area or not. If you think that you are not interested, please leave.
Yeah.
Don't continue because after some time you are going to be fed up
Yeah.
and you may not be able to do. So if you think that it is not going to help or it's not my cup of tea, take that decision. Because nowadays it was not like earlier when you have only very limited sports. Now there are many things you can think about where your interest is. But that doesn't mean that you don't complete your 5 year properly. 5 year
Yeah,
of your
once you
study
need to
has to
learn,
be
yeah.
properly done. And this will already give you then whether you are interested in research or not. If you are not interested, please don't go for it. That is certain. बिकॉज अभी जब हम 12th में ये बच्चे आते हैं इनसे पूछते हैं हाँ मैडम मुझे बहुत इंटरेस्ट है 90% ऑफ यू
Even they get admission, they'll be after you. मैडम मुझे नहीं, जन्म से यही कोर्स करना
हाँ
है.
हाँ बस ऐसा ही है और मुझे तो बहुत और मुझे तो जेनेटिक्स में ही everyone wants only in genetics. This is how you people come. But then by the time you are coming here doing this thing, धीरे धीरे वो interest slowly going down. And,
Activation energy comes down.
but then why are we here? See, CMB is trying to motivate you so that your activation energy should be always high. So do not allow your activation energy to go down. That's why you are going for training. That's why you are being such lectures are arranged so that your activation energy should be always high. So what is your status? Already gone down?
Let's thank Kaustabh for
These are my first suggestions.
Yeah.
I always love them.
you can check it, they will go down. You can track this, you can track the video.
Okay. Thank you so much.